Okay, so hopefully people can hear me now. Uh, I'll talk about anisotropic regularity. Same talk I advertised, shorter title. That's all. So what am I actually going to talk about? Uh, First, I want to talk about some motivation for my problem, which the motivation comes from minimal surfaces. And in particular, I'll talk about DeGiorgi's flat implies smooth theorem for minimal surfaces. And this will lead to a weird class of PDEs that are non-elliptic and nonlinear, and almost nothing's known about them. And in order to use them to prove regularity of minimal surfaces, I need to know regularity of the PDE in the first, of solutions to the PDE in the first place. So we'll start with that. And then I'll introduce some tools from convex geometry and Banach space geometry that have already shown to be somewhat useful for proving regularity of the solutions to these PDEs. Then I'll talk very, very briefly about the 0th order regularity. And then I'll spend more time talking about the higher order regularity, which is still a work in progress, before concluding with pointing out how much is not known about these and how many things could be done with them if we knew more. So where do we begin? I'll start with DeGiorgi, who showed a flat implies smooth theorem, just like the Allen-Caffarelli theorem that Max Engelstein talked about, says that if you have a minimal surface and you zoom in at a point where your minimal surface is flat, then you're actually, for area minimizers, you're analytic. For almost minimizers, you're C1 alpha near that point. And the way that the story goes is once you zoom in far enough around this flat point, first, DeGiorgi shows that 99% of the minimal surface is a Lipschitz graph on a smaller scale. Not just any Lipschitz graph, you can make it a Lipschitz graph with arbitrarily small Lipschitz constant. And because of these two facts and the fact that you're a minimal surface, it turns out that this function also is almost harmonic. Harmonic functions are very nice. And combining all of these things, you can set up a Campanato iteration to show C1 alpha regularity of the minimal surface. But now I'm going to emphasize where the harmonic function comes from. So you have your set of locally finite perimeter. We'll skip the intermediate steps and actually just assume that our boundary is a graph. So first of all, we define the perimeter of a set of locally finite perimeter by just integrating over the reduced boundary. And what you integrate, you take the Euclidean length of the outward pointing unit normal vector. And after a very long computation, you realize that the Euclidean length of a normal vector is 1. And so this gives you exactly the perimeter of your set. And so it makes sense to define this as your perimeter. But then if you assume that this perimeter functional, your boundary is the graph of some function u, you can rewrite your perimeter just like you would in Calc 3. And you can rewrite this perimeter as some property of your function by using the surface area formula that you've all taught your own students. And now anyone who's ever looked at calculus of variations will tell you the first thing you should do to understand this is compute the first variation. And so if you compute the first variation of this functional, the square root of 1 plus du squared, you get the aptly named minimal surface equation. Perfect, so far so good. Everything seems reasonable. But before we get distracted with hard nonlinear PDEs, we remember we have a specific goal in mind. So we're going to remember that our solution is a Lipschitz solution. So we have that our gradient is in L infinity. And because of this, we consider the coefficient matrix A of x, that's the identity matrix divided by the square root of 1 plus the gradient of your solution. This is an elliptic matrix. And because of the fact that we're Lipschitz, well, it's elliptic because of the fact that we're Lipschitz. It's trivially bounded above by the identity matrix, but due to the Lipschitzianity of our solution, it's also bounded below. But this isn't the only thing that DeGiorgi lets us do to cheat. Well, first of all, this was DeGiorgi's motivation for his contributions to the DeGiorgi-Nash-Moser theory, because here you have a elliptic divergence form PDE with L infinity coefficients. But also we get to cheat further and not worry about that right now, because we also know that our function has really small Lipschitz constant. This will allow us to tailor expand our coefficients. And now the identity divided by the square root of 1 plus du squared is actually just the identity plus some really small error. And this is where harmonic functions come from. This is why they play an important role in the theory of minimal surfaces, because our minimal surface equation in the small gradient regime is basically the Laplacian. So this is the motivation in the classical setting. Are there any questions before I switch to the anisotropic world. All right, so let's consider a new type of energy minimizing surface. I'll put the LP norm on the perimeter of my surface. So we do the exact same thing. We consider a set of, well, maybe. We consider a set of locally finite perimeter E and some opens at A, and we look at the energy of E inside A by integrating the outward pointing unit normal vector, but this time we take the little LP norm of it. Turns out, naively, at least I thought, that if P were really close to 2, you could do some sort of compactness contradiction argument and just steal regularity from area minimizers. And this doesn't work at all. You don't converge to the area functional in a nice enough way for that to help in any way, shape, or form. So this is a completely different problem that is more difficult than I originally thought it would be. But let's just try to do this game of DeGiorgi. So we'll go ahead and assume that our perimeter is a graph. Then we can once again rewrite our energy in terms of properties of the function. You can once again perform an outer variation, and we get what should probably be called the anisotropic minimal surface equation. Unfortunately, this doesn't look as nice as the last one, but we at least have an idea of what we should do. So we'll introduce a coefficient matrix, just like we did last time. So we'll define the matrix A of X to be the identity, this time divided by this slightly worse denominator than we had before. And once again, thanks to DeGiorgi, we might as well for now assume that we have really small Lipschitz constant. So not only is this going to be an elliptic matrix, it is also going to be approximately equal to the identity. And this allows us to hopefully make the same kind of simplification as DeGiorgi, because now our anisotropic minimal surface equation gives us a new PDE that when I first saw it, I didn't know has been studied, but this is sometimes called the pseudo-P Laplacian. So it's something people have looked at before. That's very exciting. It has a little bit of regularity theory, just not quite enough. So if we look at this equation in the weak form, this is how you could write down the pseudo-P Laplacian. It's shown by Francois Demangel in like 2014 maybe, that the solutions are Lipschitz. It's not the P Laplacian because we don't have the full gradient. We only have single directional derivatives at a time. And so therefore the directions in which we fail to be elliptic, there's a lot more of them than there are for the P Laplacian. So we should expect it to be worse behaved. So it's known that in arbitrary dimension, solutions are at least Lipschitz. In dimension 2, there have been recent works from 2020 that show that in dimension 2, you're C1 log. And that's the best that's known about regularity of this relatively easy to write down PDE. Harmonic, part of the reason harmonic functions are so nice is because they also come from a minimization problem. So we could ask ourselves, does this also come from a minimization problem? And it turns out that it's precisely the Euler-Lagrange equation of this energy. So we have hope that it's not just a random PDE, it's also a minimization problem. Hopefully something good can still be said even without ellipticity. And between looking at these two expressions for long enough is where I decided to generalize, where I decided to eventually come up with the class of questions that I've been studying lately, which can be stated more or less in the calculus of variations language. You can ask, what is the regularity of minimizers of this functional, where you take an arbitrary norm rho and some homogeneity coefficient gamma. You just apply your norm to your gradient, raise it to the power of gamma, and that's the way you define your energy. And we want to understand those minimizers. If you compute the outer variation, then that's equivalent to asking what is the regularity of weak solutions to this PDE. This PDE doesn't look as nice, but I claim that it's actually easier to talk about in a 30-minute talk. So I'm going to focus on the PDE side of things today. But since the PDE doesn't look so nice, let's start with some examples. So the most obvious example to do is if you choose your norm to be the Euclidean norm and gamma to be 2, then our PDE is exactly Laplace's equation. Okay, that's good. If you change gamma to be P and keep the Euclidean norm, you get the P Laplacian, also good. And where did we start? We started with the pseudo-P Laplacian. If you change your norm to the LP norm, then you get the pseudo-P Laplacian. Well, DeGiorgi's motivation was elliptic divergence form PDEs. So let's consider the norm defined by inner products with respect to some positive definite matrix. Let's choose gamma to be 2. And then we cover the wonderful class of constant coefficient divergence form elliptic PDEs. And if it wasn't for these 2 words, I'd be pretty excited about that. But the constant coefficient ones aren't quite as fun. So before we go too much further, we'll generalize our class of PDEs one last time. And for each point in our domain, we'll define a norm on that point. And this will allow us to then consider a PDE that looks more like this. And I'm gonna, from after this point on, I think always actually suppress the dependence on the sub X. So it'll look just like before, but we remember that it can change if we want it to. And now we're allowed to make our family of norms be a family of inner products with some elliptic matrix with L infinity coefficients. And now we truly recover all divergence form elliptic PDEs from this family of PDEs. Another one that's near and dear to my heart, because it's my motivation, was if you choose gamma to be P and you choose your norm this way, after having a solution, then we actually recover the anisotropic minimal surface equation for the LP norm. And so this means even some of the not yet satisfactory regularity results that I've been able to show already tell me things about minimal LP minimal graphs. And so I'm starting to get to the end goal, but there's a long ways to go. I guess before I go on. So any questions about this family of PDEs or anything I've said? Okay, so why do I think we need new tools? It's very common in PDE theory to say, well, this is just degenerate elliptic. And then you try to take the elliptic theory and just stretch things a little bit further. And people have actually done a great job doing this. However, there's one big problem. If you compute the Hessian of the LP norm and plug in any standard basis direction, your largest eigenvalue is your smallest eigenvalue is 0. Your entire Hessian is 0. And this means you're extremely far from being able to be elliptic. And this happens for every standard basis vector and every ray through the origin and the standard basis vectors. So the set of degenerate directions is unbounded, and there's also a lot more than just these ones. And so unlike with the pseudo-P, unlike with the P Laplacian, you can't just try to you don't have to only worry about what happens when your gradient is 0. You have to worry about what happens anytime your gradient points in certain directions. And I just don't see any way to ad hoc put this together for such a general class of PDEs. And so I think we need something new, and something that has so far proven to be useful is duality. So given some Banach space X and with the norm rho and some homogeneity gamma, you can define the gammath dual vector to some vector xi in X by taking your norm raised to the gamma divided by gamma, compute the gradient of that thing, and evaluate this at your vector. This doesn't necessarily look like a very nice thing, but it turns out it has nice properties, especially when paired with the dual norm. So in the space of Banach space, or in the language of Banach spaces, it's literally just the dual norm. But in Euclidean space, people sometimes call this the Finchel conjugate to your original function. Yeah, I'm not going to worry too much about being proper about talking about dual pairings, but when I use the inner product notation, I actually usually do mean a dual pairing, but that doesn't matter for the talk. So how do these things work well together? The first is homogeneity. We know that, stealing from Max Engelstein's, the bread and butter of GMT is homogeneity. And we have some of that here. So we have some tools that I'm used to because I don't actually do PDEs. This is more of an accident. So the homogeneity was a good thing to find. So if you compute the gammath dual vector of xi, and then take the dual norm of that, you actually get the original norm, the primal norm of xi raised to the power of gamma minus 1. And things don't stop there. You also know that if you take the inner product of your gammath dual vector with the original vector, you get the norm of xi to the gamma. And so these two homogeneity properties I claim you should think of as being similar to lower ellipticity, because you can at least use them in similar ways. You also have Finchel's inequality, which I think is, especially the way I wrote it, fairly obviously an analog of Holder's inequality. You can just take dual pairing of a dual vector and a primal vector. And if you apply the correct norm to the correct vector, you get Finchel's inequality as an upper bound. And this, combined with some of the homogeneity, you should think of as being a replacement for upper ellipticity of your PDE. And then finally, if you have a C1 norm that is strictly convex, it turns out that its dual norm is also C1 and strictly convex. And this is very convenient for not having to state hypotheses on both the norm and the dual norm. But in particular, if you just assume that rho is C1 and strictly convex, you can write the identity on your Banach space X as a composition of these dualizing functions. So if you take Holder conjugates gamma and gamma prime, and take the gamma-th dual of a vector, and then take the gamma prime dual of the dual vector, you get back to where you started. And you can do something similar on the dual space. Of course, things go funny when gamma is, when gamma is equal to 1. So here I'm always assuming gamma is greater than 1. When you try to use Holder conjugates on the endpoints, things always go funny. But the equivalent when gamma equals 1 is you can take the gradient of your dual vector, apply that to the gradient of your vector, and it spits out the identity divided by the norm. So this is also still very useful to know. And combining these three things, you can actually, they're all you need to do all of Moser iteration for every single one of these PDEs in one fell swoop. And I'm not going to do that because no one wants to see that, especially in a talk. But, oh, that was going to come later. But I'll do the Kochopoli inequality after a second, because that one's a lot cleaner. So why do I introduce these dual vectors? We just saw several properties that are nice about them. But one last property that I hope is convincing to people, at least with a minimal surface background, that these should be important, is that DeGiorgi's original till excess to decay can be realized as a dual pairing between dual vectors and your primal vectors. And this is also called the Bregman divergence sometimes, but I'm trying not to introduce too many things at once, so I wrote it this way. And it really shows that I think these convex geometry and Banach space geometry tools are the correct analog when you leave the natural Hilbert space setting. Okay, so a Kochopoli inequality. I think this is something we all have probably seen a proof of in the usual elliptic case. I claim it's no harder when you're looking at these PDEs. So how do you prove this Kochopoli inequality? Every math talk needs one proof. This will be it. Luckily, it fits on half of a slide. So you'd do the same thing you usually do. You choose your test function to be your solution multiplied by some cutoff function and compute the derivative. Because of the product rule, your derivative has two parts, a part where the derivative hit your solution and where it hit the cutoff function. Both of these will eventually go in this inner product. So when we put the blue piece into the inner product, what happens? Well, we use the homogeneity of our PDE to say exactly what it equals. We don't even have to bound it below. We know exactly what that inner product is. When you put the red piece in, you then will apply Finchel's inequality, use homogeneity, rearrange some of the scalars, and you can say that the inner product with the red piece of our derivative is bounded above by this thing. And due to homogeneity one more time, we know that this pink piece, if we get to see the whole thing, there we go, is exactly equal to 1. So therefore, we get a very clean expression that, plugging back into our PDE, tells us the integral of, I don't need the inner product anymore, eta to the gamma rho du to the gamma is bounded above by the integral of rho u d eta to the gamma minus 1. And then you'll get a rho. That's not a rho. This is a rho eta du to the 1. And all you have to do now is apply Holder's inequality with a gamma prime here and a gamma here, and you've proven the Kochopoli inequality. These are the same tools that you need to do all of Moser iteration. So if you can do this, and you can find enough ways to rewrite one in terms of gamma and gamma prime, when those are two at least, you can do all of Moser iteration, and it's just tedious from here. So that's my first theorem, is if rho is C1, that's probably a hard color to read. If rho is C1 and strictly convex, then you can do all of Moser iteration, and you can get all of the regularity results you'd expect. You get a Harnack inequality, Holder continuity, strong maximum principle, Louisville type theorem for global solutions, and as a consequence of that, a Bernstein type theorem for LP minimal graphs. Not what I wanted to talk about today, but it's proof of concept that these duality tools will be useful for showing regularity. I want to emphasize that we only require that rho C1 is strictly convex because those are really the minimal assumptions you can put on rho in order to even make sense of the PDE. Because here we need the derivative of our norm. And you know from calculus of variations that if you don't have something that's convex, you have no hope at regularity. So having strict convexity of rho is a minimum assumption to hope for regularity. And that means this whole theorem only depends upon the homogeneity of the problem. Otherwise, it depends upon the minimal amount of things you need to make sense of the problem, plus the homogeneity, and you get all 0th order regularity of your solution. Okay, so now instead of giving you definitions and crossing them out, I'm going to give you a characterization of a definition. There's a concept of the sigma convexity of a Banach space that goes at least back to the 1930s, but 1989 was characterized by saying that the difference of the dual vectors paired with the difference of primal vectors can be bounded below by the norm of the difference of the primal vectors to the power of sigma. And that sigma is why it's called sigma convexity. And this first term here is just to make sure things scale appropriately. There's another notion of Banach spaces called the smoothness of the Banach space that's also characterized similarly. You can say that a Banach space is tau smooth if the dual norm of the difference of dual vectors is bounded above by the primal norm of the difference of the primal vectors raised to the power tau minus 1. And then you once again need something here to make sure things scale correct, or else you have no hope of having an inequality. Okay, so for the 0th order regularity, you don't need basically any assumption on the norm. I hope that in order to get a convenient higher order regularity result, making assumptions about the sigma convexity and the tau smoothness of the norms are the correct things that you need. And I have 8 minutes, okay. And we have some progress. Since these are all new things, maybe not, prototypical examples are the LP norms. That's where we started, of course. So when P is bigger than or equal to 2, the little LP norm is P convex and 2 smooth. And the little LP prime norm is P prime smooth and 2 convex. And this is prototypical of Banach spaces and their dual Banach spaces because the P convexity leading to the P prime smoothness of the dual happens in general. And then in this case, it's the 2 smoothness leading to the 2 prime convexity for the dual also happens in general. Okay. So what can we hope to do with these things? In 1987, there's a theorem of Bojarsky and Iwaniak for the P Laplacian that said if you take this nonlinear function of your gradient, you can actually show that this function of your gradient has a weak derivative. And so this is like a way of saying your solution has a very weak second derivative. So before we get too far along, let's note that if you take the absolute value of f of x, that's exactly equal to the gradient of u raised to the power of p over 2. So the fact that you get W1, 2, this 2 here is just because P over 2 times 2 is P, and you knew a priori that your gradient of U was in LP. So it's not the integrability that we really care about in this statement. It's the existence of the derivative and being able to make this coefficient as non-degenerate as possible. So how do they do this? Most of the proof isn't necessary. The important thing is they have these 2 elementary inequalities that also the details aren't super important because I want you to at this point blur your eyes a little bit and compare them to the notions of sigma convexity and tau smoothness. So without looking at the actual numbers, you notice that the first inequality they use, they have some nonlinear function of their gradient paired with their gradient differences of their gradient is bounded below by the nonlinear quantity of their gradient. And here we have the same thing for sigma convexity. Here we have a difference of dual vectors. We have the actual vectors, and we're bounded below by something. Other things don't add up, but it's morally equivalent. And same for the second inequality. It actually matches up better because here they have this term that at first looks really bizarre, but it's just there because it has to make sure that the homogeneity is correct. And that plays the same role as the maximum over here. And so when I saw this, I actually had recently made this realization, and I gave a talk at the Max Planck Institute, and a professor came up to me afterwards and said, I think it's very naive of you to believe that it's something as simple as the dual of the gradient will be what has regularity. They told me to compute it by hand, which sounds way harder than just guessing that the dual is the right thing. So I still didn't really follow their advice. I asked them if they wanted to compute it by hand, and they ignored that. So I went ahead and kept thinking about what I was thinking about. And Lukas Koch, also at the Max Planck Institute in Leipzig, who's actually trained in calculus of variation, started working with me. And we were able to show that if you look at a solution of this PDE, where you assume that your norm is sigma convex and tau smooth, then you can show some regularity of the dual vector. I want to point out at this point that I basically think of my PDEs as a family of PDEs parameterized by three things. They're parameterized by the homogeneity, the smoothness, and the convexity. And so here we're able to show that the dual vector to your gradient is in this lovely Besov space, which in short means you gain an alpha proportion of derivative. And you gain that much, and alpha is exactly the minimum of your homogeneity and your smoothness minus 1. In particular, for the P Laplacian, your smoothness is 2, your homogeneity is bigger than 2, so you gain a full derivative. If you look at the primal derivative, you get also an alpha proportion of a derivative. This time you have a worse alpha, where alpha is now the minimum of your homogeneity and your smoothness divided by the maximum of your homogeneity and convexity. So this alpha is only ever equal to 1 if gamma equals sigma equals tau equals 2, which is exactly when you're looking at elliptic equations. So at least these techniques don't seem to give us a full derivative of the primal gradient, a full weak derivative of the primal gradient, unless we're in the elliptic setting. But we can at least get a full weak derivative of the dual to the gradient without being in such a restrictive setting. And so if we compare with the result of Bojarsky and Dubaniak, you see that here we have this du to the p minus 2 over 1 instead of over 2. So indeed, the gradient goes to 0. This is more degenerate than the expression by Bojarsky and Dubaniak. So we didn't quite recover as much differentiability as they did, but it's proof of concept. And since then, I've tried to recover their result, and up to at one point showing that I need p to both be less than 2 and bigger than 2, I was able to do it. So I need to check my inequalities. But there's hope that we can recover this sort of result as well. So this leads us to open questions in future directions, of which there are a whole lot. So first, I'm just including the PDE. So as I keep talking, you can look at it if it makes you happy. The immediate question that I'm working on is what conditions on gamma, sigma, and tau can imply that this particular dual vector of the gradient is in W12. And this is what would give the exact analog to the Bojarsky-Dubaniak result. Another question that has been inspired not by me is, are there better functions to consider of the gradient? I don't even know where to start here. So if someone who's done like nonlinear potential theory or something has a good idea, I'm all ears, but I have no idea where to start with finding other nonlinear functions of your gradient to study. Maybe hopefully a more tractable question is, do certain values of gamma, sigma, and tau imply that your dual gradient is Lipschitz? A lovely thing about this is if your dual of your gradient is Lipschitz, then so is your gradient. And that would make me very thrilled, especially because we know that for the pseudo-P Laplacian, the solutions are all Lipschitz continuous. So this much at the very least I think is achievable. And hopefully the nearish future. What would make me the most happy because of the application I have in mind is to find some condition on my parameters to make it so that my dual gradient is C1 alpha. Unfortunately, this does not tell me that the gradient is C1 alpha. So there'd actually still be work to do, but maybe the best you can do is expect regularity on the dual gradient, because in elliptic problems, those two things are basically the same. So maybe every statement you've ever seen about the smoothness of your gradient is actually a statement about smoothness of the dual of the gradient. And then one other trick that would be nice, since it seems the dual behaves better than the primal, is could you do some sort of PDE constrained measure thing, come up with the dual statement to that and recover the primal gradient? I tried that for a little bit, no great success, but is something that seems like it could be promising. and at least help narrow down the constraints on your parameters for knowing what are the right things to try to look at. If you could get C1 alpha regularity of solutions, using the variational approach to regularity of the optimal transport map that was recently introduced by Felix Otto, Maxine Prudhomme, Tobias Reed, and I should have written this down because I'm forgetting at least one person. I would expect to be able to extend the result of regularity for optimal or for general cost functions. They get regularity if you're in a C2 alpha neighborhood of the Euclidean cost, which is better than just the Euclidean cost, but that's a very strong norm to need to get Holder regularity of your transport map. And if we knew C1 alpha regularity of these things, you could then get regularity of all costs that involve norms raised to some power. And you just have to keep track of what's the homogeneity of your norm and what's the smoothness, convexity, and homogeneity of your cost that way. And finally, what I fear is going to be important for studying regularity of minimal surfaces is to understand anisotropic mixed growth problems. Because even with the LP norm, I can't understand all of the graph solutions by only knowing what happens to the pseudo-P Laplacian. So mixed growth conditions might become important. And then this would be where you see that P being closer to 2 does actually help you out. All right. I went 2 minutes over, so thank you for your attention, especially right before lunch on the Friday. So.